turbine just don't like water droplets. So we need to have superheated steam there. Most of the time on the end of LP turbine, in most cases, we are somewhere in the wet steam area, so we will have there some water droplets in. We need the cooling water for removing the latent heat, so the heat which is getting free during the condensation process, and then the circle is starting again. Of course, bypass stations in for HP, in this case IP and LP, to when the steam turbine is not in operation yet, or when there's a problem during startup, yeah, that the steam quality is not adequate for the steam turbine, so temperature is not high enough, you're not enough superheated, conductivity or something is bad, yeah, then we're not running it on the turbine yet. Then we saw the melting and vaporizing process. So the quantity of heat you need for this process, yeah. So melting is needing more quantity of heat than, let's say, changing the ice cube from -20 to 0 degrees, yeah. The same then for the vaporizing process. So this vaporizing process needs a lot of quantity of heat, so a lot of energy in here. And that's why we also trying then in an supercritical power plant where we over the critical point, because there is no vaporizing phase anymore. There's a direct change from water to superheated steam or to steam. So there is no wet steam area anymore. So here melting process, we have the boiling, that's what we have. Normally over here then somewhere your tea boiler is switching off. Then we have the vaporizing and the superheating, of course, when you have superheated steam there. We saw the critical point. For each pressure, we have a corresponding boiling temperature, yeah, and these values are normally saturation pressure and saturating temperature. There is also then a big table in. I just show it on the another one. Just a second. So it's looking like this. That you have here the saturated steam table, and the saturated steam table is giving you for each pressure, so saturation pressure, the corresponding temperature table. Over here it's now, yeah, from 0 degrees, yeah, 0.061 bar absolute, so really low pressure, yeah. Power plant normally 0.05, depending where you are. This is normally a good value, 0.04 sometimes, yeah. And then we're going up, we have at 1.013 bar, the 100 degrees saturating temperature. This is our normal ambient temperature where the water is boiling at 100 degrees. We saw this fast cooker with 2 bar, yeah, 120 degrees Celsius. And then when we're going up, the higher we're going with the pressure, the higher the saturation temperature getting. Yeah, so at 100 bar, we are at 311 degrees, and this is going up to 221.2 bar. This is our critical point with 374.2 degrees Celsius. So until this critical point, there is a so-called vaporizing phase and a wet steam area. And above this, there's a direct phase change from water to steam. And that's also what you see then in this TS diagram, which I showed yesterday. So normally when you have normal water, you're taking it out of the tap somehow with 20 degrees or something, the water boiler heating it up, and you're coming here to 100 degrees. And then it's important the steam, the vaporizing is happening at the same temperature. Yeah? So the temperature is not rising over there or changing, it's happening at the same temperature. So here we have then the so-called wet steam area. Yeah, so over here 100% water, over here 100% steam. The last water droplet vaporized, and in between is the whole thing, the whole area is called wet steam area. We have here the blue lines in. The blue lines are showing how much steam is in there. Yeah, so when I go here in the middle, I have 0.5, so I have 50% steam and 50% water still in there. The further I come to the right side, the less water is coming, the more steam. Here 90% steam and then 100% steam. Over here we've been 100% steam. So 100% steam, then everything would be good for the steam turbine. But we're saying here, normally we superheating the steam. So when I bring more energy into the steam, then I'm superheating the steam, and I can superheat here on the same pressure curve, so still 1 bar, can go up here and say I'm superheating my steam to 400 degrees. Then I have here steam is 1 bar, 400 degrees, and therefore my steam is 300 Kelvin superheated. I have here 400 degrees, 100 degrees. So steam temperature minus saturated steam temperature is giving me my superheating value. But I'm not doing it on 1 bar because over here, this phase is pretty long. It's taking a lot of energy in. So what we're doing on a power plant, we're increasing the pressure, and the more we're getting up here to probably 100 bar, the shorter the area of the wet steam is. So the less energy we putting in here, and the less energy is in there, yeah, it's of course better for the process. And on a supercritical power plant, for example, with 300 bar, you can see you're getting over here on top on this green line, and you're not having a wet steam area anymore. So you have here water, 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 and then changing over to steam, and then the steam is superheated. And this is of course good for the power plant because this wet steam area taking lot of quantity of heat, what we saw, energy in there for the vaporizing of water, and this is not in there when you have a supercritical power plant. But therefore, of course, you need to get to 300 bar, you need to make everything safe to 300 bar, etc. So that's for this one. So that's why we say here critical temperature. So critical temperature is really, well, critical point is really important for some power plants, yeah, when they are running in the supercritical values. Otherwise, just explain 80 bar, 380 degrees. Is checking here, going down to the curve, yeah, curve telling you 295 degrees. So the superheating is 85 Kelvin. And this is what you do in the power plant. Yeah, you're checking that your steam is adequate superheated, and also the steam turbine during the startup is checking these values because we want to avoid wet steam in the steam turbine. And that's why these superheated, this saturated steam curve is somehow in the logic in, and then the system is comparing it, taking the pressure for the adequate pressure, you have a temperature value, saturating temperature, and then the saturating temperature will be compared with the actual temperature you have in there. So actual steam temperature minus saturated temperature, and you got your steam superheating value, which for the steam turbine should be normally higher than 30 Kelvin. So we also had already fast boiler, yeah, or pressure cooker, increasing the temperature, and therefore your food is boiling at a higher temperature, and therefore it's boiling faster, yeah. So instead of boiling at 100 degrees Celsius, when you go to 2 bar pressure, 120 degrees Celsius, so your food is cooking much faster. This one we had then yesterday too. So temperatures, like we just saw on the saturation curve in the TS diagram, yeah, vaporizing. The water over here is 100 degrees. You get the steam bubbles in. The steam has 100 degrees. And here on top, when it's condensing again, the steam has still 100 degrees over here. So then, of course, further states when you have 120 degrees, closing it. That's what we had with the pressure boiler over there. And then there is a 2 bar pressure inside, and you still have the bubbles in. Then was the why we need or why we're building a condenser, yeah. So condenser has some functions in, yeah. So we have the example, we played it through yesterday. We saw when we have a condenser in, first of all, this is the big point, we don't have any water losses. We have some water losses, yeah, because it's a closed circle, so you need to exchange some water, but we don't put the full amount of water to atmosphere like without a condenser. And the water is demineralized water, so it's pretty expensive and difficult to produce. So we want to save there as much as possible from it. And we got also a higher power output because we go not only to 1 bar atmospheric pressure, so we go into the vacuum area, and therefore we have a higher enthalpy drop, which was going down here to 2333, and therefore the higher enthalpy drop and then higher power output. You blow it to atmosphere, which was, let's say, in the start phase of the steam turbines. This was the first way, and also you have it probably on the steam ship, yeah, that they just blowing it into atmosphere, yeah. They're not condensating it in there. We have the high water losses. We have less power output on a modern machine, so roughly half the power output from a machine with condenser. And this is, of course, why we're using condenser. Condenser, we see here cooling water, so the latent heat, which is getting free, needs to be transported away. When it cannot be transported away, you cannot keep the pressure here, so your pressure will increase. And when the pressure is increasing, your enthalpy drop is decreasing, and therefore your power output from the turbine will be getting lower. So the temperature here is important when you have cooling water with, for example, 30 degrees, and you bring here steam in with 30 degrees, there's nothing happen because the condensation cannot happen because it cannot transport the heat away. Same temperature, cooling water cannot take the heat away. So there need to be a certain temperature gap in between that the water can take up heat, transporting it away, and the condensation process is happening. Normally something like 5 to 7, 10 Kelvin difference in there, so that the cooling water can really take the heat losses away. So then we saw the efficiency from the power plant. Yeah, it's depending on what you gain divided by the input. Yeah, what we gaining is over here on the generator. Yeah, So this is what we're gaining. We have here the discharge of heat. This is the output. And then we have this, what we're putting in there. So everything putting in is, of course, our exhaust gas from the gas turbine. This will go into the condition. We have here our condenser again. We have the pump in. We have then supply of heat for the preheater, evaporator, superheater, and then getting into the steam turbine. Steam turbine is transferring it into rotation energy onto the generator, electrical energy, and then we have here the condenser with the latent heat, so our discharge of the heat losses. And then we can come here to a value. So efficiency 1 minus T out divided by T in, and there's something like 65% coming out. For the components, we have the mechanical components, the valves, control valve, to control the amount of flow, for example, into the drums to keep it level, for example, for the drums, everywhere where we have control valves in. So throttling the flow and the right way so that it's really controlled way. We have open and close pipes, so gate valves blocking the way then, Like I said, gate valves always with a small bypass around. The bypass is there when you have here on one side 100 bar standing on, second side is empty, that there the forces on the gate are reduced. So when you open the gate up and it's 100 bar on one side, 0 bar or 1 bar on the other side, you have a high velocity and high forces on the gate. Can lead to bending of the gate so that it's not properly open or closing anymore. And this is avoided with the small bypass. So the small bypass can handle these pressure differences and then filling up or pressurizing the second side or the outlet side of the gate valve. And when the two sides are equal pressure, we can open up the gate. We don't have any velocities over the gate. We don't have pressure difference over the gate, and the gate is easily open up. This is also always within the logic, normally inside the boiler, when you have the big boiler gate valves, they always have the small bypass, and then when the pressure difference is probably under 5 bar or under 3 bar, then you are able to open up the gate valve. Safety valves, of course, everywhere where we need to protect from overpressure. So that can be a spring one. There are various types, and so the spring force is set up to a certain pressure here in the system. And when the system pressure is getting over this setup pressure, the force from the system is getting higher than the spring force, and the system is open up. Then as soon the pressure is low enough again, the safety valves should close again. Then we have the flaps in here, and the flaps are for, let's say, low pressure system, cooling water system, where we have not the biggest pressures in there, not the highest velocities, and then can also open or close piping, shutting it off. Restrict flow, we saw yesterday steam traps, mainly in the drain lines when you have there an drain valve and in parallel a steam trap in. So in case during operation there's some condensate coming, the steam trap will automatically drain the line without the need of opening of the drain valve, where the risk is there that you're taking steam into the drain system, and this we want to avoid. Non-return valves is clear, I think. So everywhere where we want to restrict the flow in the, let's say, in the direction there are non-return valves in. For example, on every pump, normally you have it on the steam extraction from the turbine, yeah, so just to avoid any backflow then into the turbine when it's there. The orifices to limit the flow, so it's like a small hole in there. There's variation in from the hole size. There you can calculate the flow through the orifice, and then you have this in. We saw pumps then, pumps, mechanical device, yeah, increasing the speed and pressure. Two main types over here, yeah, so one-time displacement type pumps can be this piston pump, there can be a gear pump, this is all displacement pump. So mainly create the flow pressure by moving the medium from one temporary closed space to the next one. You see it here, you're taking the medium in, then it's closed over here, compressing it and putting it then on the outlet into the system. So you have temporary closed spaces, and therefore there are very or a lot of different types for displacement pumps. And centrifugal pumps are over here. So centrifugal pumps with an impeller in here, and you have one constant flow through there. Yeah, so you can also, let's say, fill up through a pump which is not running. Yeah, because the system is more or less open over there. You don't have a temporary closed space. And all this is depending then, of course, on the pump restriction, safety, etc. So here you have a continuous flow. Here you have the temporary closed spaces. Then you need to protect over here, of course, for min flow. Yeah, so there on a centrifugal pump, always a min flow line in. Over here, you need to protect for the overpressure in there. You have the conditions for starting up, yeah, for the centrifugal pump we heard yesterday, NPSH, so the net positive suction head, yeah. So we need a certain suction side pressure for the pump to start. And for these pumps, normally they are own suction, so they don't need the pressure in there. For example, an oil pump, you have them in the oil tank in, there's the line in, and they start running and taking the oil in. So there's no need for a certain suction side pressure. Heat exchanger, tube bundle heat exchanger. The big one we have is the boiler. You have the LP heater normally, and then we have the plate type heat exchanger, for example, loop oil system for with the closed cooling water system on the generator, etc. wherever in the system. Yesterday we had opposite flow direction to have a low temperature difference and heat exchange over the full range of the cooling plates here. And otherwise, when you have same flow direction, you have at one point and pretty high temperature difference and therefore an high heat transfer to the cold side, so fast heating up. And then on the half of the heat exchanger, probably you don't have any heat exchange anymore because the temperatures are probably equal already. And then we saw here dam and water tank, yeah, with the sheet I opened up yesterday. So level protection sheet where you have level measurement. You have various tanks in there. So dam and water tank is an atmospheric tank, yeah, so it's open to atmosphere, but of course there with a filter, so-called breather on top, so that the air can go through, but no dirt particles coming in, because we have here demineralized water in there, so we don't want to get any dirt particles in this water. But of course, we need to make sure that when we pumping out water, yeah, that the tank is not sucked in, yeah, or when we put water from the production in there, then that the tank is not pressurized at this point. Ignition gas tank for storing gas, accumulators in the fuel line for stabilizing the fuel oil over here. Yeah, so when there's some pressure drop in the fuel oil line, the accumulators have a certain amount of fuel oil stored in here. Then in most cases is a nitrogen bladder in here. Question? Hassan, is there a question? So there's in most cases a nitrogen bladder in or an air bladder in, yeah, which you can fill up with nitrogen before when the system is off. And then the oil will be during operation getting in here. It will be stored in there. That's why it's called accumulator. And when the system pressure then on the downer side is dropping, the nitrogen bladder has the higher pressure and pushing the fuel oil, which is stored in here, into the system. So pressure drops can be avoided or extended. Yeah, that there the system is not tripping out when you have, for example, pump trip and changing over to the pump, and the second pump needs a moment to build up the pressure. Compressed air tank, so pressurized tank, yeah, storing the compressed air. There are, of course, safety valves on that we protect it against too high pressure. Otherwise, it's storing here a certain volume of compressed air in what inside the power plant will be taken out then, and then with the compressor refilling the tank here. This storage tank. A drum, so the drum in your case, let's say you have the IP and HP and LP drum. So HP drum, of course, separating main function, storing feed water over there, and then also, let's say, separating water and steam. And then the LP tank, of course, also storing water, because it's in your case something like a feed water tank. Yeah, so it's a drum separating water and steam, but at the same moment, it's the connection to the feed water system. So the feed water will be taken out of the LP drum, and therefore it's like a storage tank and for the feed water system. And then we have the loop oil tank with all the pumps, coolers, etc. Mounted on them already. So this is during the test phase. And then you have here the high volume of oil in, also for storing and making sure, let's say, reducing the cooling volume, yeah, because it's only a smaller volume which you need for the steam turbine, but you have a big volume of oil in, so dirt particles can lay down, and also you have lower velocities in there, and you have a big volume, so it's not heating up that fast when you're sending the oil to the bearings where they heat it up. We saw the cycle process, yeah, so condenser here will be sent with pump into the boiler. The boiler will produce our steam. The steam will be sent to the steam turbine. Steam turbine is connected to or is coupled to the generator. Generator is producing our electricity, which we are selling, where we're getting the money in, and then getting back into the condenser and getting condensed. For the Sankey diagram, so that's the process diagram for a combined cycle. So we have here our fuel amount which we're getting in. So that's 100% fuel. That's the let's say that's the part we are paying. Yeah. So best thing would be we paying here for 100% fuel and we getting 100% out. Then we have the highest efficiency, yeah, but that's not working. So for the gas turbine over here, we're getting normally something like 40% out, yeah. So 40% is the torque to the GT generator, and therefore, let's say inside the turbine needs to produce 80%, because 40% are taken by the compressor. So half the power of the turbine is taken by to run the compressor. And then these 40% are left over here for the electrical output on the GT generator, and 60% of the energy is getting into the exhaust gas. On an open cycle unit, this one would just go exhaust gas temperature over the roof out, yeah. In a combined cycle, we're trying to use as much as possible with the steam turbine. This is normally 20%, so that you come in a combined cycle to this round about 60%. Can be on some power plants just 55. The newest or modern ones, they getting to 63, 64%. Yeah, so there's every percent is of course important nowadays. Then we have here the big part, condensing energy. So you see 31% is still getting out with condensing energy. So this is something or most power plants at the moment are not using. Yeah, so this is just for the condensation process. The thermal energy, let's say, which is heating up the cooling water, around about 31% of the amount, and then 8% for the exhaust gas temperature, where we have limitations how far we can go down because of the condensation of the NOx gases on the boiler, which of course should be avoided, because otherwise you have corrosion on the boiler tubes, and this of course we want to absolutely avoid, that the power plant can run for long term. So this ranking process, again, saw it before already. So left side the process, right side the TS diagram, so temperature entropy diagram. And then we see over here first is with the pump, the pressure increasing. This is one time happening, let's say, yeah. Condensate pumps or feed water pumps, this is our pressure increasing. Then it's getting into our boiler, and the boiler taking the hot exhaust gases in. And there we have, first of all, preheating phase, we have the evaporation phase, and we have the superheating phase. And this is what we have normally for, in your case, HP and LP. From there then, from the superheating, we getting onto the steam turbine. In the steam turbine, we transferring, we have the expansion expansion inside the turbine blades, transferring energy into rotating energy, generator producing then electrical energy, and the steam pressure will be reduced, the temperature will be reduced, and then we're getting here into the condenser, and inside the condenser, same temperature, condensation happening, latent heat or the heat getting free will be transported away with the cooling water. And this process is then going on. This is the circle process. When there is reheating over there, then we can say we going to the feed water pumps, yeah. Then we have the preheater phase, we have the evaporator phase, and we have the superheater phase, then getting onto the HP turbine. And when you then have enough energy still in the HP steam, when it's out of the turbine, we sending it into the boiler again, we reheating it to get rid of the risk of wet steam. Yeah, so when you're getting at this point, you have probably 350 degrees, 35 or 35 bar roundabout in a Siemens power plant, and then we're saying we reheating it in the boiler again. So we're using energy from the boiler, getting up to probably these 600 or 550 degrees again, and then getting into the LP turbine, getting down, and then there's the condensation process happening again. This should be clear from the basics so far. So then we started with the system. So we had first of all the condensate water system. So the condenser over here with the condenser level, getting one time the makeup water over here, which is controlling our level inside the condenser. Makeup water coming here from the right downer side from the dam and water system. Yeah, so dam and water pumps, which one pump is always running, also supplying here into the system for filling up during standstill or keeping it under pressure during standstill. And then it's also going to vacuum system, closed cooling water system for refilling. So from the condenser hot well, we're going then to the 3 condensate extraction pumps. These are 3 times 60% pumps. Yeah. So normally 2 pumps are running. Increasing the pressure. We see then later on with the barrel pump design, getting here to sampling system, dosing system, and then over here one time for the spray water for the flash boxes, external flash box and internal flash box, where let's say all the drain lines are getting in. And when you're coming there from probably an HP system drain line, you have an high temperature in there, high pressure in there, high temperature, draining out to in the flash box. If the flash box or the drain tank is normally open to atmosphere, so it can happen that your condensate, because when it's under, let's say 80 bar and 250 degrees, condensate, but when you bring it now into 1 bar area, atmospheric area, it will steam out, and so you're getting steam in there, and that's why you have spray boxes in there. So you're spraying condensate in there to cool down the steam before it's then getting into the condenser. Then we have the spray water for HP bypass, same thing over here, cooling down the steam for right condition to get into the pipe, into the condenser. We have the
Mr. Sufyan,
yes, sorry.
if we don't have external and internal flash box, what does this affect on the condenser and the vacuum?
Let's say normally you have something like a standpipe on there. When you don't have it, it can be that you're bringing steam into the condenser and steam into the condenser. So it depending on the temperature you're bringing in there, but when the temperature is pretty high, it can lead to damages on the condenser tubing, because the condenser tubing is not designed for steam, let's say 250 degrees or 300 degrees Celsius. So that's why you have normally, I will open it up. I have one picture from it. Give me 1 second. So So that's how it's looking. I mean, it's not the best quality, it's just a picture. So you have here normally this external tank, the PDN internal tank, yeah, and then it's getting onto the condenser. So you see here HP steam pipe, bypass drain, steam pipe. So there's a lot of temperature getting in. And what you're trying to do with these, it's more or less a standpipe, yeah, or this tank. One time when there's water coming in, or condensate coming in, the condensate will directly be connected to the condenser hot well. So it's getting into the condenser hot well, mixing with the water which is in there, and the steam which is over here getting in, probably 151 degrees, yeah, probably steaming out. This will go over here in the condenser steam part. And then, of course, you want to make sure over here, let's say that the condenser over here, getting it then into the tubes, but the temperature should be so slow or so low that the condenser can handle it. Because normally, let's say when the steam from the steam turbine is getting into the condenser, this will have 30, 40 degrees probably, yeah. So you have your pressure over here is 100 kPa. 100 kPa is 0.1 bar. Sorry, I'm always counting in bars, yeah. And when you're checking 0.01 bar, just to make sure, 0.1 is 46 degrees, yeah. So you have a normal steam temperature in there from 46 degrees. And when you're there now, suddenly bring steam in with 150 degrees, then the condenser can be either overloaded, it can be that you're increasing your pressure in there, yeah. So what you're doing here in this steam line, there is normally the spray water line connected. So you're just spraying condensate in there. Condensate will be sprayed in, it will cool down the steam, and the condensate will just go in this tank and go then into the hot well. And you have condensate, so it's clean, so it's no problem. And then let's say the steam here will be cooled down. So it's then getting in the temperature which is acceptable for the condenser. And the amount, let's say during normal operation, of what you're getting over here is nearly zero. Because the drain lines are normally only open during the startup phase, yeah. So during startup, you're getting here a high amount of condensate, probably steaming out, but during operation, all these HP steam lines are for sure closed because there's superheated steam. As soon as there's superheated steam, there is no chance or no risk anymore that there could be any condensate coming in there in the line. So the system is checking the conditions in the line when you have here HP steam pipe, and it's saying here you have there 80 bar and 400 degrees in, then you're superheated, and then it's saying here to the drain line, the drain valve over here, drain valve will be closed. This one will be closed. So during startup, all the drain lines will be open because we don't want to have any water in the steam line standing, because this could lead to big problems for the piping. Yeah, I mean, we heard it yesterday already, steam expanding. Yeah, so steam volume is around about 1,700 times the volume of condensate or of water. So when you have here a steam line and you have the water standing in, the water will suddenly expand. And this could lead to pipe bursting, etc. So we have everywhere in the system the drain lines in, and the drain lines need to be opened during startup to remove the water out of the pipe. normally after shutdown, they will be already open up to really remove everything out of the line so that there can be only steam getting in. Then the boiler or gas turbine is started, the boiler is producing the first heat, and then the drain lines are open. So there will be condensate accumulating over there because the steam pipe is still cold. And when you're bringing steam on a cold surface, then exactly where we have it, this one is happening. So you have condensation on the piping, yeah, because the piping is still cold. You're bringing steam in. Condensate is getting on the cold pipe. It's condensing. The steam is condensing, and this water we draining out then. And this water will be drained out of the system, and then getting here into these tanks. Yeah, so the external and internal tank. External tank normally because it's everything from the boiler. Boiler is for this system an external one. And then you have here the internal tank where everything, let's say, from the steam turbine is coming in. So you see here steam turbine drain line, seal steam line, gland steam line, gland steam line from turbine bleed. Yeah, so this is all turbine internals. They're just splitting it up to make sure, let's say, that you have the pressures equal, that you have the header lines there. Normally on Siemens, yeah, I need to say it, on a Siemens power plant, let's say you have a drain tank on the boiler side so that you have the pipelines, the pipings from the boiler somewhere inside the drain tank at the boiler so that you have shorter pipings over there. And then you have pumps and pumping it away, yeah. And this one is then pretty near to the condenser, so it's getting into the condenser, but also with pumps on the Siemens side. Over here, they're making it pretty near to the condenser. So the drain lines from boiler side, they could be pretty long then, yeah, because they're coming from the boiler. And therefore, let's say, getting in here. And for the question over here, the question, to come back to the question from Saif, if they are necessary, I would say it's making life easier when you have a tank over there. It's possible. I mean, this is not, yeah, it's a tank. I mean, in Siemens, we would probably call it an standpipe. Yeah, so just to make sure separation from steam and water, because otherwise you have the connection and then you're bringing condensate into the steam side. This is not nice, and you bringing steam into the hot well is also not nice, so that you have this separation in from steam and condensate. Okay. Then getting further here, there is a layer inside the pipe that it forms when the oxygen content tries to preserve the pipe. Okay. Saif, can we put this one back? I mean, what you're going for is from the chemical cleaning. Yeah. I will search something out because I think it's not in here with a detailed description, and will answer it after the lunch break because it's not directly related to this part now. But I will explain it to you because it's a chemical part, let's say, yeah. and therefore I search out some foils that it's getting, some presentation that it's getting a little bit more clear. Okay, so we were over here. So here also LCA. Then we have here the Gland Steam condenser, the bypass for the Gland Steam condenser. So Gland Steam condenser. So we have on the steam turbine, we have a steam ceiling on the steam turbine, and there from the glands, the steam, which is there, let's say, getting away, this steam will be condensed again, and over here on your power plant for the condensation medium, they taking the condensate. On other power plants, they taking the close cooling water, but here the condensate to get the heat, let's say, into the system, and then of course the bypass over here. We have the LP heater, bypass of the LP heater. LP heater was yesterday also a thing. We coming there later, and then we splitting up to the two boiler over here. And when we see then condensate system, extraction of condensate out of the condenser hot well, forwarding the condensate to the systems we just said, seawater system, external and internal flash box, HP steam bypass desuperheater, LP heater system, Gland steam unit desuperheating water, and condenser water, certain spray water. Cooling the Gland steam condenser, condensate extraction pump min flow is discharged back to the condenser. We have a centrifugal pump, so we need a min flow line. This one is led directly back to the condenser. Heating of condensate by steam turbine extraction steam at the LP heater for GT fuel oil operation, and 2 out of 3 condensate extraction pumps, each 60%, then critical parameters, filling and venting of the system before start of the pumps. So system always need to be filled and vented then before starting the pump, and this is what's happening normally with the Daemon water over here. So you're filling up the system here, closing here probably everything on the LP heater, filling up the system here, and then over here, let's say there are vent lines in venting the system. Hussein, Ali, and Ali. Function of the LP heater. I would say in the operation manual, it's saying preheating of the condensate before the boiler. That's the condensate preheating. I'm not fully sure yet. I asked my colleague yesterday. He said, it can be necessary because you on your power plant, the LP drum is, let's say, has a double function because it's not only an LP drum, it's also at the same moment the feed water storage tank. And for the feed water pump, you need normally to have a certain temperature in the system. And therefore, it can be that with the preheater alone, because the preheater, which we have then, which is coming, let's say here after the LP heater. Let me check, there was the preheater. Preheat. Exactly. So we have then here, let's say coming from the condensate, here is somewhere your LP heater in, and then there is the preheater coming. So the preheater is at the end of the boiler. Yeah, so it's one of the last layers. It can be that during the operation, because the LP heater can only work when, of course, the steam turbine is in operation, because before that, you don't have steam from the steam turbine to run the LP heater. So it can be that during some operation conditions, let's say, you're not getting enough heat out of the preheater over here. So the preheater is here to preheat, let's say, your condensate before it's getting into the LP drum. But probably it's not enough temperature in there anymore because you're at the end of the heater, so it cannot take enough energy out of the preheater there. And therefore, let's say the LP heater is more or less supporting it, because when you bring here, already yesterday somebody said it's like 70 Kelvin heating up. Yeah, so when you bring it in from 30 to 100 degrees and bring here already 100 degrees in, and then you need then the preheater needs a smaller amount getting in, yeah, and then getting into the LP drum. It's not a standard design for Siemens, so I never saw it before, and the manual is not telling in which condition really the LP heater is coming into operation. So I'm guessing that it has something to do that the preheater here alone is probably not able to bring the amount you need probably for the feed water pump then, plus recirculation and reheating it at the same moment to get the right temperatures for the LP drum, or then let's say feed water storage tank here. And that's why at one point the LP heater will come in. Hassan? But I mean, you're there on site. Is the LP heater running when the power plant is on base load, or is it running on certain conditions? Or was it until now never running? So that's in the manual LP heater. Yeah, LP heater is to use the latent heat of vaporizing of steam condensation to heat condensate water. Vent pipe is to vent uncondensate steam and non-condensing gas from the LP heater. But there's not written in when the heater will be switched on and when it will be off. So they have here design criteria in, yeah, LP emergency drain, flow velocity, materials in, but startup, yeah, that you first starting up the water side, which is clear, yeah. I mean, the water side, it is running in the base load. Okay. So then normally I guess the amount of steam or preheating, let's say, which the preheater can do during this baseload case, yeah, that it's not enough and that the LP heater gets in to more or less support the preheater for preheating. This is my guess, but I will check again with my colleague. He was just flying to a project, but that's the normal case then, yeah, that it's supporting over here. So you're taking steam out because otherwise probably over here you cannot reach the temperatures necessary for the feed water pump over here, yeah. For the feed water pump is over here. And then probably this is, here's feed water pump, yeah. For the feed water pump, and therefore you need to have a certain temperature amount in there. So that's what I don't know it from our pens. We on the combined cycle never had an LP heater somewhere in. So, and the documentation you saw it is not telling it. But when you say it's running during base load, then I guess it's something like this that you're getting there, or without the LP heater, not getting the temperature conditions in there. Okay, so that's therefore we were what are okay, Saif. So what are the operational errors that increase the vibrations on the turbine? Also for pumps. So you mean on the steam turbine, what can happen or what could increase vibrations over there? I mean, therefore, let's say you have the steam turbine training, but of course, what could increase vibrations, not the right amount of oil in, so that the bearing, let's say, getting their vibrations, the general alignment of the machine, yeah, probably the alignment, the expansion from the machine, there are many various in, yeah. The steam flow into the turbine, probably stacking control valve, yeah, that you have different steam flows in there. There are a lot of parts which could increase this part. Bearing damages, yeah, bearing wearing off, this is all what could go in there. And for pumps, the same, yeah. I mean, you have the bearings in there, you have then the flow amounts in there. So when there's something happen with the impeller, with the blading, yeah. I mean, vibrations on the turbine, we had it coming over here. So when you have cavitation on the pump, yeah, the impeller on one side or on two sides, material will be taken off. So you have imbalance in, and then of course the vibrations are increasing. So these are the normal effects that can go in there. From operational errors, there I would say it's for the steam turbine at least. Operational error, only one I would say is the sampling system. So when you don't take care of the sampling system, say your steam quality is not as it should be, then this can of course lead to errors, because there the operator need to act, because you're getting a warning but you don't get a trip. So you're getting alarm, yeah, that the steam quality is not adequate anymore. You have in the steam turbine a big table in how bad the steam quality is allowed to be, but there's not an automatic stop of the steam turbine. For everything else, I mean, when vibrations getting too high, the steam turbine will trip out, protecting itself. When oil temperature is getting high, turbine will trip out. When both loop oil pumps will be switching off, electrical error, you have the emergency loop oil pump getting in and the turbine will run out. Yeah, so there most of the errors are protected. It's just normally steam quality, let's say, where no trip function is in there. And for pumps, yeah, I mean, when you're running a pump out of the line where it's working, let it be too high flow, too low pressure, etc. And at one point, it's probably running and not pumping anything anymore. Yeah, then this is also a problem. Opening the vacuum breaker at high speed, the vacuum breaker is blocked, so you're normally not able to open it without, let's say, getting into the logic and setting some forcings. Of course, when you're opening up the vacuum breaker at full speed, it could be that you can collect some blades out of the condenser. Because what you are doing is you're suddenly increasing the vacuum to ambient conditions in most cases, yeah. And therefore the forces, especially on the last blade row, so the longer blades is increasing massively. And this can lead then, let's say, either to vibrations or it can lead, let's say, really to ripping off of blade row or blades and then extreme vibrations, yeah. Of course. But vacuum breaker, I mean, operational errors, it's normally protected. Let me see at 1300 RPM. Yeah, even at 1300 RPM, it's for sure not good. So normally on the machines, it should be blocked till I think 6 hertz or something. So 360 RPM or something should be the limit for the vacuum breaker to open. But I don't see this as an operational error. Yeah, operational error. The system is blocking it, the vacuum breaker from closing. Yeah, and everything else, either you need to force it open. Yeah, so operator need to have the forcing rights to say in the logic, okay, I'm overwriting the close signal. Yeah, and then open it up manual. But you should not touch it. Normally, even on it's there, the vacuum breaker is there to increase the vacuum during an emergency shutdown. So for example, fire at the turbine. And therefore, we want to run down the turbine as fast as possible so that when firefighters coming in and the turbine is still running with 2500 RPM and there are parts flying around, yeah, then it's not safe. So we want to run down as fast as possible. And the vacuum breaker is then also not open fully. It's open slightly, yeah, to increase the vacuum, let's say from 100 kPa probably to 200 kPa or 250 kPa to increase, let's say, or decrease the vacuum and therefore giving more resistance so your turbine is running down faster. That's the function normally of the vacuum breaker. So it's not there to open fully. It's really there, let's say, to increase the vacuum and therefore giving a high resistance to the LP part and then faster shutdown of the turbine so that it's safe for firefighters probably who coming there, that can run, and also for the turbine itself with the emergency rundown, you have the emergency loop oil pump running, and the emergency loop oil pump has only a certain time running, normally at least half an hour or something. That's the minimum. And in this time, the turbine should be run down. And when you have a good turbine in vacuum, it can take an hour 15 to run down. Yeah, that's always depending on the turbine. Okay. So Saif, I hope that's answering. And the other question I will search out for after the lunch break. So with here a critical process parameter, filling and venting of the system before the start of the pump. Condenser level low for CEP and PSH. So that was a thing we had yesterday. So inside the condenser, you should have the low level, and the low level should give a signal to the CEP pumps that they getting and protection of signal to protect the turbine from cavitation over there. Signal should be in, I said should be in. I don't have the full documentation, so I don't know if everything is really in, but it should be in the system to protect the CEP pumps from one time, of course, from cavitation and also from steam breaking through. Yeah, this is also a fact, because when you don't have water in the condenser, then there's probably steam in, and the steam will be sucked into the condensate extraction pump, and that is also not a good way. Then we have conductivity by circulating water leak at the condenser. So that's meaning you have your tubes in the condenser. The cooling water is running through, and this tube is leaking. So what you're getting cooling water into the condenser, and therefore let's say you have your conductivity measurement, and then you can see, okay, something is wrong on the condenser. The conductivity is getting wrong, so there's a problem over there. Same conductivity corrosion by air ingress at the condenser. So that's when you have somewhere a leak at the condenser. You have a vacuum inside. Air in, air meaning oxygen in, and oxygen is not good for the process over here. Main component enable and protection circuits. Yeah, that's the protection. So condensate extraction pump enable to start. Condenser level must be higher than min. That's what we saw yesterday. I showed you the example from an dam and water tank, yeah, where we have the typical protection sheet there, level protection sheet, and then condensate extraction pump protection. That's a typical one. So we are, or I'm not having the documentation where you're saying here the in your power plant it's this and this. So Hussein, I'm sorry I cannot tell you the exact values. I didn't receive the full documentation, and so I don't have the information how much the MPSH of the CEP needs to be. The easiest way to find out is when you get into the system, yeah, on the HMI over here, checking for the pump. On the pump, there's a protection coming in. It should come from the level here, and then it's probably saying, I don't know, 200 millimeters or something, yeah, during operation, and then you have the value in there. For me, it's more important that you know, okay, there is a value there, and we also see it in a moment when we get to the pump. Yeah. So condenser level less than min, yeah, CP discharge pressure less than min, CP suction strainer delta P higher than max. So when the strainer is full, you're creating an suction side pressure over there, yeah. So then the pump will be protected, changing over to the second pump, and then of course motor winding temperatures and bearing vibration and bearing temperature. So these are the normal protections you have or you should have in the pumps. And then of course condenser level protection, so level higher than max. So when you're getting mainly from base load to a lower load, then you have an too high water amount, let's say in the water steam circle in, and then the discharge valve needs to open. Yeah, the makeup water valve is already closed, and normally when you have the level load less than min, the CEP pumps will trip to mechanically protect the pump from cavitation. So cavitation we saw yesterday. So you have the impeller in there, you have here downstream of the impeller, and then at the impeller, let's say you have these air bubbles building up because you're near to saturating temperature, so there's more or less steam building up. And then the further you're getting over the impeller, the static pressure will increase because the pump will increase the pressure. That's clear. So the bubble, cavitation bubble will implode and you're getting these jet from the surrounding liquid. So the water will create a jet and getting onto the material. And this can lead to big damages on the material. So it's like a gun getting in there and taking material out of this impeller. And this, of course, we want to avoid. For the CEP pumps, we doing this by increasing the NPSH. So we putting the pump further down with this barrel design. We minimizing the cavitation risk. Despite the low suction head, yeah, because over here you have somewhere your condenser, you have the condenser level, and then with this small part you would have a too low NPSH. So what we're doing, we're going here 2, 3, 4 meters down, increasing the suction head, and then on the downer side, let's say you have the impeller and then the riser pipe, and then you're getting out here with the increased pressure. So that's how we doing it over here. Of course, the protection there with the level, this should be in. I mean, yesterday somebody said it was, you were running with, I think, 270 millimeters and there was nothing happen yet. So probably it's at 250 or 200 millimeter, but somewhere it should be in to protect the pump. Because otherwise, really, you have the problem, probably even getting steam in here, air in here, etc. This can also lead to problem. So that's the pump then. So you have here this design. This is normally on 0 meter on inside the pit then, yeah. So in the condensate pit, you have here inlet outlet side. You have here normally then this part in with the bearing, the motor support, and the sealing, yeah. So this is the blue part over here. And here on top, there is then the actual motor coming on, yeah. So there's a lot, really huge pumps over there, yeah. But this is also always depending on the design, yeah. So can be that it's these big pumps, it can be because of the flow that they are a little bit lower. This is just an example for one pump. And then you have here on the downer side, let's say the booster stage for the third part. And there can also be that the impeller is specially hardened to protect it against cavitation. Yeah, can be, don't have to be, because with the barrel design, let's say we're trying already to minimize the risk of cavitation. Okay, so good. So then we had the LP heater drain and vent system. Yeah, so the LP heater is in here. We have the emergency drain line, which is then going to the condenser. We have here the LP heater drain pumps, which getting into the condensate system, and then the actual LP heater, where the steam is getting in from the steam turbine bleed, and then a vent line, of course, to vent the line, the heater before the operation or during the operation. So it will be before the operation, it will be evacuated. And then, of course, you have the condensate as a more or less cooling medium getting through the heater, and the condensate taking then the condensation heat, yeah, so the latent heat from the LP heater, and using it also as a small, as a preheater over here. So for the process description, yeah, draining of steam condensate to the condensate system downstream of the LP heater, venting non-condensable gases back to the condenser. Heat rate is a variable of the LP heater condensate level, and 1 out of 2 LP heater drain pumps, what we have over here. Critical parameter, LP heater level low for pump, NPSH, and steam lock. So that's the same again. You have here your LP heater drain pumps. You need to have a certain level inside the LP heater, because otherwise you have the same problem. You have here centrifugal pump, and then you got the same problem that you don't have NPSH pressure here, and probably you bring steam in here. Steam can then go through, and you're getting the steam probably directed to the pumps. When the pump is then getting steam instead of condensate, that's of course not good for the system. Yeah. Then we have LP heater level high for extraction steam line production. Yeah, this is a problem when you're getting steam. You're taking the steam, the bleed steam out of the turbine, and when you get a level high there, yeah, so then it could be, let's say, that there's steam, let's say, not getting from the turbine anymore, or probably even backflow, let's say, into the turbine as a worst case, and then, let's say, also getting there the protection there. Erosion risk at the emergency drain outlet. The main component enable and protection circuit, so drain pump enabled to start, is of course our LP heater level. There must be a certain level in. Drain pump protection, heater level lower than min. LP heater bypass operation in case of the LP heater not available trip. So when the LP heater is not available, then of course bypassing it, and the stream extraction protection close when the LP heater level is higher than max. So then we're saying we switching off the steam turbine over here, the bleed line, and saying here for protection, the LP heater will be not, or there will be no steam sent from the LP heater to the, or no steam from the steam turbine to the LP heater. Now, okay. So that's how far we got yesterday. Questions from your side? I mean, LP heater. My colleague said also he's thinking it's something like a preheater in a steam power plant, that you normally just not getting enough heat from the preheater, and therefore that you're getting there, let's say, these LP heater to make sure you're getting the right heat for the feed water system over there. Because during startup, let's say when steam turbine is not in, there's not the problem, but probably later on when you have full flow, the preheater cannot take enough heat out of the exhaust gas anymore, and therefore over here there is this LP heater in. Okay, so then we go one step further, just a couple of more minutes, yeah, then it will be your lunch break. So we have the preheater recirculating system, yeah. So preheater recirculating, so this is for pre-warming the condensate for the HRSG. So flue gas temperature control is the big factor, yeah. So you have a certain sulfuric acid dew point. So that's what I said yesterday already with the NOx, let's say in general set point. So you need to have a certain inlet temperature into the preheater, because this is the coldest piping, yeah. So when your exhaust gas is getting over there and the inlet temperature of the preheater is too low, there it will, when it's under the sulfuric acid dew point, the sulfuric acid will condensate over there, and therefore you're creating acid corrosion from the exhaust gas side on the piping there, on the heat exchanger piping. And this, of course, should be avoided. So therefore, there are 2 out of 3 pumps over here, so preheater recirculating pumps. And the preheater recirculating pumps, they controlling this temperature over here. So this is the inlet temperature to the preheater, and this inlet temperature needs to be so high, so over the sulfuric acid dew point. And that's depending if you're running, let's say, with gas or with oil, yeah, because for oil, this dew point is much higher than for gas. And then it's depending on the gas quality. So let's say a really clean gas, you are somewhere at 55 degrees, and then normally going up to 70, 80 degrees. And for oil, you are somewhere over 100 degrees, 100, 110, 120 degrees, which you need to have there to be over the sulfuric acid dew point. So the system is running. You have here the 2 recirculating pumps. It's normally running in full automatic control. So it will get normally an defined set point, temperature set point over here for the inlet temperature. And then the system automatically controlling over here the flow, which needs to be going there to get the set point. Exactly, this one we had, and then protections in there, of course, in that valve, enable close if all pumps are off. The recirculating pumps, when some temperatures are there, yeah, bearing temperatures again for the pump, winding temperature, motor winding temperatures, etc. This is all in there again. So that's an typical design. Same here. I didn't get any or received any documentation from the pumps, how the pumps looking like. So normally for Siemens power plant, let's say we have these recirculating pumps, yeah, one stage impeller pumps, suction side, outlet side, yeah, and there are 3 pumps in parallel, and then just recirculating the water from the outlet of the preheater, so where it's warm already, to the inlet side again. These 300 degrees Celsius sound for me pretty high, but okay. And then, of course, you have a preheater bypass, and the preheater bypass, which we have over there. So this one is making sure that we have here behind the preheater normally no steaming out before we getting into the LP drum. So there should not be any steam condition or vaporizing there, yeah, where before we getting into the LP drum. So it's mixing then colder water again with the hot outlet water here to get a sufficient temperature here to the LP drum. For the process description, yeah, pre-warming the condensate for LPHRSG in addition with the LP heater. But here more the flue gas temperature control, sulfuric acid dew point, yeah, internal recirculation by the 2 out of 3 pump operation and 2 control loops, so recirculation and cold. Critical process parameters, venting before pressurizing, steaming after hot shutdown, yeah, trip. The main component enable and protection circuits, yeah, inlet valve, enable, close if all pumps are off. Recirculating pumps, enable on, so condensate preheater inlet open. Motor bearing less than 85 degrees Celsius. Pump bearing less than 100. Motor winding temperature less than 135. And then protection off when the delta P of the strainer is higher than max. When the motor bearing is higher than 95 degrees Celsius. When the pump bearing is higher than 110 degrees Celsius. Motor winding temperature higher than 145. And when the HAA 85 AA101, that should be this control valve over here. So when this one is under 2% for 3 seconds, so it's closed, then the pump will be switched off, because then we're saying we don't need the pump running anymore, and therefore the pump will be off. What's also important is here preheater outlet temperature control. Yeah, so normally LP temperature or saturating temperature -2 Kelvin. So we are pretty near to the saturating temperature, slightly underneath it. So 2 Kelvin underneath, and this will be controlled here with the cold bypass and the outlet temperature over here, so that here the temperature will be near saturating temperature, and then let's say you have the maximum heat taking out there, getting into the drum, and from the drum then into the evaporator. Okay, so that's the next one then. Are there questions from your side?
No, son.
Okay, so then I would say we make the lunch break. We didn't make a break in between. We meet again at 1 o'clock, and I will check for the question from Saif